Let's look at two more disk method examples. Find the volume of the solid formed by revolving the region bounded by the curves y equals square root of x plus 5, y equals 3, x equals 4, and x equals 0 about the line y equals 3. I want to get some accurate points in here to make this easier. So I'm going to start with 1, 2, 3, 4, 5, my starting point for my square root function. Then I go the square root of 1 is 1. The square root of 4 is 2. The square root of, well, I could go 9, but I don't really need to because of the boundaries. Y equals 3. 1, 2, 3 on the y-axis. Here's where y equals 3. X equals 4. 1, 2, 3, 4. Vertical line x equals 4 is right here. And the vertical line x equals 0, that's the y-axis. So what's important here is that I shade the region that's touching all of those curves that I just drew. So I'm going to shade, and perhaps lightly so it's easy still to see the curves. Okay, so I'm going to shade in there, touches all those lines and curves. And then I'm going to see what is the axis of rotation about the line y equals 3. Here's the line y equals 3. I draw it nice and bold, maybe a different color, and I show with my little swirly that to remind myself it's going around that. Then to make it look three-dimensional, I graph some reflection points. 1, 2, 3, 4, 1, 2, 3, 4. Just want to make sure it's in the correct places. And there, and there, and lightly, lightly, lightly do I shade the reflection, or in a different color. Then we tell ourselves, what is volume? Volume is the integral of the area of a slice of this solid. How am I going to slice this solid? Always perpendicular to the axis of rotation. Our slice will be perpendicular to the axis of rotation. So I can either just visualize it in my head or literally draw the slice. Now, if I want to draw it circular to imagine, okay, this is going to be a disc, I could do that. Maybe I'll do it in a different color. And then I ask myself, well, what type of shape is this? This is a circle. So the area of that slice is pi r squared. I don't want to make it look like I'm dividing by pi r squared, so I'm just going to rewrite my integral. Pi r squared. Now, because it's a horizontal axis of rotation, this will be with respect to x. My slices are going in the x direction, from circles here to right, to right, to right, to left, go whichever way you want. Well, that means I need a radius. So I'm going to say my radius, let's see what it looks like from my axis of rotation up to the function, or to wherever the function is. If it happens to be down, we go down. Then I think, well, my radius is going up and down, so that means I need to find the length by saying top minus bottom. The top is the curve square root of x plus 5, square root of x plus 5. The bottom is the line y equals 3. So on top, I have y equals square root of x plus 5. On the bottom, I have y equals 3. So that's the top minus that's the bottom. We can simplify this a little bit, square root of x plus 2. Now that I have my radius, I'm going to go plug it into my volume. Integral, actually I like to take pi out, then integral, my radius is square root of x plus 2, square the radius for pi r squared, and then say with respect to x. Now all that's left is to find my limits from this x value 0 to this x value of, where's that? 4. 0 to 4. Now again, whether you do this by hand or you do this in a calculator, you'll integrate and come up with your answer. Now please be careful if you're doing this by hand that you want to use your algebra properly. If you're going to square this, this is x plus 4 roots of x plus 4 because we have to distribute, or FOIL as is popularly known. Either way, we end up with 136 over 3 times pi. Let's try one that has a vertical axis of rotation. Our solid is bound by the curves y equals x cubed, y equals 8, and x equals 0. So let's start at 0, 0. 1 cubed is 1. 2 cubed is 8. 2, 4, 6, 8. I could go this way, but I didn't give you room on your function for a specific reason. It's because we are not going to need that side. There's my cubic. Y equals 8 is right here, and x equals 0 is right here. Now remember, I lightly shade the region that touches all of those curves, and there it is. Now I see what's the axis of rotation, and it says the y-axis. So I trace over the y-axis, and I say I'm going around this. Then I draw my reflection. Here's a point reflected to the left. Here's a point reflected to the left, and I can take my time to try to draw that reflection. I think I can do better than that. I'm going to try one more time. That's pretty okay. There's my reflection. Now, remember, what is volume? Volume is the integral of the area of a slice, the area of a cross section. How do I slice this time? Well, if our axis of rotation is going up and down, I slice right and left, always perpendicular to the axis of rotation. So here is where my disk is now. If I know it's a disk, then I can say this is the volume is the integral of pi r squared, because the area of the slice is a circle. Well, now this time my slices are being piled up and down on top of each other in the y direction. So that means I will be with respect to y. Or I think to myself, if it's a vertical axis of rotation, I know that I'll be going with respect to y, like the y-axis. Let's look at one radius. I'm going to show my radius always from the axis of rotation out to the original curve. That's over here. And if my radius is going horizontally, I think to myself, my radius will be measured right minus left. Well, on the right is this function that's called y equals x cubed. But we determined that we need to be working with respect to y. Remember that the right side is an x value, the left side is an x value. The x-axis moves right to left. So I want to solve this for x. X equals y to the 1/3. So on the right side is x equals y to the 1/3. On the left side is x equals, what's on the left side? X equals 0. Now, I'm not plugging in these equations, I'm plugging in what x equals in terms of y. So my radius is y to the 1/3 minus 0, or to simplify, y to the 1/3. Now I can plug my radius into my integral, pull the pi out because it's not needed inside, it's not a variable. Y to the 1/3, the radius gets squared, and it's with respect to y. Now I just need my limits. Well, if I'm looking at going up and down, the lowest of the y-coordinates is 0. The highest of the y-coordinates in the region is 8. So 0 to 8. We can do a little bit of simplifying before we do antiderivatives, y to the 2/3 dy. And again, whether you do it by hand or using your calculator, you should get 96/5 times pi. Pretty cool, right?